A single misconfigured network interface sends an error. Within milliseconds, the frame multiplies, flooding every connected port until the entire enterprise infrastructure stops responding. This cascade effect is characteristic of a flat network. In this architecture, an entire unsegmented Layer 2 environment operates as a single, unconstrained broadcast domain. When a switch receives an Ethernet frame addressed to the all broadcast destination MAC address, the FFFFFFFFFF address, its default function is to forward that frame out of every active port. If those frames circulate through a loop, they propagate endlessly. This creates a broadcast storm that saturates bandwidth and blocks legitimate traffic. Beyond traffic congestion, flat networks lack internal boundaries. Because every node shares a common ARP table and neighbor discovery space, a compromised device can resolve and reach any other asset in the enterprise without passing through a gateway for inspection. To secure and scale these communications, enterprise architecture moves away from flat topologies. This transition requires logical segmentation, explicit traffic tagging, and managed redundancy. Physical infrastructure remains an operational liability until it is constrained by the logic of specific networking protocols. The architectural solution begins by taking physical hardware and dividing it logically. This is achieved through virtual LANs, or VLANs, which segregate departmental traffic directly at the data link layer. By assigning specific switch ports to distinct VLANs, the singular broadcast domain is divided into smaller, contained zones. This diagram shows vertical boundaries separating engineering, marketing, and accounting VLANs. A broadcast frame from engineering cannot reach accounting, isolating nodes on the same switch. To move data across these Layer 2 partitions, traffic is forced upward to a Layer 3 router. Forcing traffic through a Layer 3 device allows administrators to apply access control lists and specific security policies between departments. By deploying VLANs, a single physical switch functions as multiple isolated logical networks. Enterprise environments often span hundreds of switches across a campus, requiring high-capacity fiber optic bundles to maintain connectivity. This presents a technical conflict. To pass multiple isolated VLANs across a single shared physical uplink, a trunk, the data needs a way to remain distinct. The industry addresses this through the IEEE 802.1q protocol, the standard for VLAN trunking. Observe the connections labeled tag. When crossing a trunk line, the switch inserts an 802.1q tag into the header, identifying its VLAN. The receiving switch reads the tag, removes it, and forwards the payload only to ports assigned to that specific VLAN. Without 802.1q tagging, maintaining logical segmentation across physical hardware boundaries would be impossible. Enterprise networks must also maintain high availability. To survive a cable cut or a hardware failure, the architecture must include redundant physical paths. However, connecting multiple switches with redundant cables creates a physical loop. In this triangle formed by switch A, switch B, and switch C, a loop is present. Because Layer 2 lacks a time-to-live mechanism to drop aged packets, broadcast frames will circulate and duplicate indefinitely, triggering a broadcast storm if unmanaged. Switches use the spanning tree protocol. They elect a route bridge, identify the lowest cost path, and place a block, the red X, on redundant links to break the loop. If a primary link fails, STP instantly restores the standby redundant path to maintain connectivity. While STP prevents loops, it also leaves redundant cables idle. To use that extra capacity, organizations implement IEEE 802.3ad Link Aggregation. Link Aggregation bundles multiple physical cables into a single logical link. This increases total throughput and bypasses the STP blockages while preserving the failover capability. STP and Link Aggregation work together to provide the necessary failover and data throughput required by the business without risking a network collapse. From these granular protocols, we can see how the optimized enterprise system functions as a cohesive unit. This full view shows the Layer 2 core switch connecting multi-floor segmented departments. Each piece fulfills a specific role. VLANs isolate traffic. 802.1q tags carry that data across the backbone, and the combination of Link Aggregation and STP secures the core against physical failure. Operating a network at Layer 2 requires active management of data flow through specific protocols. Relying solely on basic physical connectivity leaves the entire environment vulnerable to the hazards of an unconstrained broadcast domain. Assess your current infrastructure. Is your local network partitioned into high-performance VLANs, or are your assets exposed on a flat architecture? Align the strategy, optimize the network. Until next time, keep your business connected, your assets visible, and your infrastructure secure.